probability events involving the word or. Our objective, we want to find the probability that a first event or a second event will occur. All right, so let's take a look at what we know. We know what probability is. It's the chance that something, an event, I got to make sure I get rid of that D, an event will happen. Okay, as we know, the probability of an event happening is always between 0 and 1, or between 0% and 100%. A probability of 0 or 0% means the event is impossible. A probability of 1 or 100% means the event is certain. We know how to find the probability of an event happening. We have to first establish the total number of outcomes, and then the numerator is the number of ways that the particular event you're looking for can happen. We have some notation. P parentheses event is notation that says probability of the event happening. And we're going to see this used, this concept or this fact useful in this video. When we add two fractions, and of course with probability there'll be proper fractions, the sum, the result is always larger. Okay, so the sum of two fractions leads to a larger fraction. Okay, that's important because of what I'm going to say next. When dealing with the probability of this or that, we are expanding, okay? We are enlarging the number of possibilities for success. And that's where this comes in. We're going to be adding two or more fractions, and that is going to be expanding the number of possibilities for success. The probability is going to be larger. Let's take a look at how that works with one of my favorite things here, donuts. Okay, let's take a box of donuts, and I'm going to draw a box. And you'll see that my drawing skills are limited, and I'm going to have in my box 12 donuts. It's going to be a box of a dozen donuts. Nothing fancy, it looks like that. And in my box, I'm going to have 4 glazed, because I like glazed. I'm going to have 5 chocolate, because I really like chocolate. I'm not a fan of jelly, but I know some of my family and friends are, so I will include 3 jelly donuts. Okay, so what is the probability of reaching into this box and pulling out a glazed? So probability of a glazed. Well, there are 12 donuts and there are 4 glazed. So the probability, if I reach in and pull out a glazed, I have a 4 in 12 chance of doing that, which of course is simplified to 1/3. I have a 1/3 chance, a 1 in 3 chance. If I reach in blindly and pull out a donut, there's a 1 in 3 chance it will be a glazed. Okay, let's talk about the chocolate ones. Let's talk about the probability of reaching in and pulling out a chocolate one. Well, I have 12 donuts. If I reach blindly in there and pull out a donut, the chances of getting a chocolate one, well, 5 of them are chocolate. So I have a 5/12 chance of pulling out a chocolate donut. Now let's see. What's the probability of pulling out a glazed or a chocolate? Okay, now notice I've expanded my possibilities here. I don't happen to like jelly. So I'm hoping I reach in there and pull out a glazed or a chocolate donut. Okay, so I have 12 donuts. How many of these how many of these donuts are glazed or chocolate? Well, this one's a glazed or a chocolate. It's a glazed. This one is a glazed or a chocolate, etc., etc. This one's a glazed or a chocolate. It's a chocolate. So I have 9 glazed or chocolate donuts. Notice I've expanded with the word or. You know, if I say, hey, if you reach in there blindly and pull out a glazed or a chocolate, you get to eat it. Well, you got a 9 in 12 chance of pulling out a donut you get to eat. Okay, now you'll notice what I did here is I took the number of glazed and I added up to it the number of chocolate. So the probability of a glazed or a chocolate turns out to be equal to the probability of a glazed, which is 4 out of 12. 4 of these are glazed, plus the probability that it's chocolate, which is 5 out of 12. And there's the 9 out of 12 that we came up with earlier. And of course, that can be simplified to 3 out of 4. Okay, so the upshot of OR probabilities, when you're dealing with probabilities that involve OR, you're expanding the possibilities. Okay, as we did here. Hey, you get to eat. If you get a glazed or a chocolate, you get to eat it. Well, that's awesome. There are 9 of those. You get to add up the glazed and add up the chocolates, and you got 9 out of 12. So we're using addition when we're dealing with the word OR. Okay, let's take a look at the 2 different possibilities as to how this works. Okay, I think you can see that. So OR probabilities come in 2 types. They come in, the first type is mutually exclusive. In other words, the 2 things have nothing to do with each other. And the second type is they're not mutually exclusive, which means the 2 things have something to do with each other. You have an overlap. Let's take a look first at mutually exclusive. Okay, let me get my paper situated here. Okay, mutually exclusive. 2 or more events that cannot happen at the same time. Okay, so we're doing one thing. You know, we pulled a donut. Okay, and there's no way that I could pull in one pick. I could pull both the chocolate and the glazed. Okay, there was no chocolate/glazed donut. Okay, so the 2 events, pulling a chocolate or pulling a glazed, are mutually exclusive. They can't both happen together. You're going to either do one or the other. And as we just saw, we solved these by just adding up the individual probabilities. Probability of glazed or chocolate equals probability of glazed plus probability of chocolate. Okay, we just saw that. Let's take a look at two additional examples. We're going to select one card from a deck of 52 cards. What is the probability of selecting a king or a queen? Okay, so probability, there's that word OR. Probability of a king, oops, I don't want to close my parentheses yet, that's my mistake. Or a queen. Okay, well, probability of as we know up here, these things, there's no way to pull one card that is both a king and a queen. No such card in a deck of cards. So these 2 things are mutually exclusive. They both can't happen at the same time. So this is equal to the probability of pulling a king plus the probability of pulling a queen. Again, I can't do both at the same time. Okay, so there are 52 cards. How many of those are kings? If you look at a deck of cards, you have 4 kings. King of clubs, king of spades, king of hearts, and king of diamonds. And you have the exact same probability or the exact same number of queens. Out of 52 cards, total number of cards, 4 of them are queens. So the probability of pulling a king or a queen, we're going to add up the 2 probabilities, and that's going to give us 8 out of 52. If you want that simplified, as a simplified fraction, that's 2 out of 13. If you want the percent, it's approximately 15.4%. Okay? Example 2, with mutually exclusive events. There were 4 boys, 5 girls, 3 men, and 2 women at the party. If one person is selected at random, what is the probability this person is a boy or a girl? Okay, probability of a boy or a girl. Well, no chance when you can select one person. There is no person that's a boy-girl. Okay, you're either going to be a boy or you're going to be a girl. There is no, these are mutually exclusive. You're not going to pick one person that says, I am both. Okay, so that means this is equal to the probability of a boy plus the probability of a girl. Okay, well, there are 4 plus 5 is 9, plus 3 is 12, plus 2 is 14. There are 14 possibilities. The number of boys is 4. There are 14 possibilities. The number of girls is 5. So we add up these because they are mutually exclusive. We have a 9 out of 14 chance, a 9/14 chance. That's as simple as it gets. And that's approximately, in percentage terms, 64.3%. So if you randomly select one of these people, the chances of randomly selecting a boy or a girl is just about 2/3, 64.3%. So that is mutually exclusive. Let's take a look at cases in which we have things that are not mutually exclusive. Okay, 2 or more events that can happen at the same time. In other words, there's overlap. Okay, we'll see how that works with our examples. It'll become pretty clear in our examples. Okay, there's overlap taking place. So we're counting something or someone twice, and we don't want to count them twice. We only want to count them once. So we're going to subtract the overlap. We solve these by adding up the individual probabilities, same. But because we counted something or someone twice, hence the overlap, we're going to subtract out the overlap. We're going to subtract out the probability of the overlap right here. Again, this makes much more sense when you see an example, and I've got 2 or 3 here. Let's take a look. A single 6-sided die is rolled. What is the probability of rolling an even number or a number that is less than 5? Okay, probability of rolling an even or less than 5. Well, I know it starts off the same way. Okay, so this is the same as probability of even plus probability of less than 5. Okay, now let's see here. My evens are 2, 4, and 6. So I have 6 total outcomes on a single 6-sided die. Of those, 3 are even. The numbers that are less than 5 are 1, 2, 3, and 4. Those are the numbers that are less than 5. So I have 6 possibilities, and 1, 2, 3, 4 of these are less than 5. Well, wait a second. If I stop here and add these up, 3, 6 plus 4, 6 is 7, 6, and that's greater than 1. That's impossible. There must be overlap. And indeed, if you look, the 2 got counted twice, and the 4 got counted twice. Okay, well, I don't get to count it 2 times. I only get to count it once. So I'm going to subtract the probability that it's even and it's less than 5. Okay, well, I have 6 possibilities. How many of these are even and less than 5? Well, the 2 is even and less than 5. The 4 is even and less than 5. So 2 of these are both. So I counted the 2 here and here. I counted the 4 here and here. So I double counted. I have an overlap, so I'm going to take out 2 of those to get rid, of the double counting. And now I'm good. 3 plus 4 is 7 minus 2. The probability of rolling an even number or a number less than 5 is 5 out of 6. Okay, and that can't be simplified, and as a percent, is approximately 83.3%. Okay, let's take a look at a more of a real life example using where you see things in kind of a table. You already have the data. And this will maybe make a bit more sense as we look at a table to work with. Let me get my paper straightened out here. Okay, example 4. Not straight yet. I think that's pretty good. Okay, example 4 here. This table shows us the marital status of the U.S. population in 2015 in millions of people. So we have males and females and totals. We have married, not married, divorced, or widowed. Okay? And so you can see here that we have 66 million men who were married in 2015. We have 15 million women who were divorced in 2015. In 2015, we had a total number of women of 131 million. And of course, our total number of people, 254 million people in 2015. So let's take a look at some examples where we're going to see, we may see some overlap. Okay, and a table shows this quite nicely. If one person is randomly selected, find the probability that the person is divorced or male. Okay, probability divorced or male. Okay, my word or there is not very good, and we know that the word or means we're adding. So probability of divorced plus probability of male. We'll check for overlap in just a minute. Okay, divorced. Well, I have a total of 254 people, 254 million, excuse me. How many of those are divorced? 26 million. So 26 million total divorced out of 254 million. Okay, I have 254 million. How many of those are male? Here's my male row. I have 123 million males. Okay, now, if you look at it, I used this column to get my total divorced, and I used this row to get my total men. If you look right here, I counted the 11 twice. Okay, I counted 11 million are men. I counted them in the 123, and 11 million are divorced. I counted them in the 26. I circled it twice. I circled it in the row and in the column, so this 11 got counted twice. Well, I got to subtract the overlap. Okay, so subtract out the divorced, I'll abbreviate that, and male. The people I counted twice. I have people that are in both categories. I have people that are both divorced and male. So I can't count them twice. I have 11 out of 254 that I double counted. I'll take out one of those double countings. I'll do the math here. And the answer is 69 out of 127 as a simplified fraction, which is approximately 54.3%. So again, once I've done them individually, I need to see, is it possible that people are in both of these groups? Is it possible to have men who are divorced? And yes, it is. Well, I counted them twice. Let's take a look at example B here. Let's not lose my chart. Okay, the person is female or married. Okay, probability that the person is female or married. Again, I'm selecting one person. Okay, this is the probability the person is female. Oops. Plus the person the probability is married. Let's do this first. Okay, the probability the person is female. I'm getting ahead of myself with these P's. We'll have 254 million, and the number of females is 131. So I have 131 chance out of 254 to pick a female. Okay, how about married? Well, I have 254 million people. The number that are married is in column 1 here, and that would be 133 million. Okay, so there we go. Now let's check for overlap. Is there anyone who is both female and married? Because I double counted those people. So here's my females. And here's my married. And you can see right there, I double counted 67 million. Okay, because there are 67 million women who are also married. So I need to subtract out the double counting, the female and married. Let me abbreviate here because I'm running out of space. So out of 254 million, I'll subtract out this 67 million because they got counted here, and I don't want to double count. And let me move this up so you can see what I've got going on. And that's going to be 192 out of 254. I guess that's doesn't make any sense. It's even, so that should be simplified, but I don't have it. Let's go ahead and do that. For some reason that came out, and let's see. Let me go ahead and do this. I thought I had it done. 192 divided by 254 as a fraction. Looks like it should be 96 out of 127. That's the simplified. And that's approximately 77.6%. So if I reach in and I want to pull out a female or someone who's married, I have over 75% chance of doing that. Okay. Last one using this table. Probably the person is married or divorced. Okay, so probability married or divorced. Well, I'm going to start out. We know we're going to add these up. Probability of married plus the probability of divorced. Okay, there are 254 million. How many are married? Okay, I'll go to my table. And there are married 133 million. Okay, 133 million are married. There are 254 million. How many of them are divorced? Back to my table. My divorce column, there are 26 million that are divorced. Go back down to here, and I'm here. Now, is there anyone who is married and divorced? Well, you're probably thinking that's kind of silly. No one's going to tell you that at the same time they're both married and divorced. And if you look here, we used the married column and the divorce column. There's no overlap at all. Okay, the person either said I am married, or the person either said I am currently married, or the person said I am currently divorced. There's no overlap. There's no, oh, I'm both married and divorced right now. No, you're not. You're one or the other. So then we are done. There's no reason to subtract. These events are mutually exclusive. So we add those up, and this answer is 159 over 254 million, which is approximately 62.6%. So there you have it. Or probabilities involve adding. And you want to, once you've done the adding, you want to take a look and see, is there an overlap? And subtract the overlap as necessary.